realized there were two parts, and I watched the second part first, and I was like,
Oh.
I don't really know where this is all coming from.
Yeah. Yeah, I'm going to have to do the same examples. I might pull some different examples out of the book instead, but let's just see.
Oh, and I heard at the beginning that you had bonus questions.
I did. I had given them I had given them this as a bonus question. Right here. So I didn't give you all that, right? Yeah, so that's why I wanted to start with this.
But if we did it, we can get bonus.
If you turn, yeah, this is a problem that I'm going to offer you as a bonus. It would have to be turned in on Wednesday before the test. All right, so what it is showing that this integral, this is an improper integral going from 1 to infinity of 1 over x to the p power diverges if p is less than or equal to 1 and converges if p is greater than 1. So you have to show that that's true. Now, I had maybe 4 students from the other class turn in this problem as a bonus, and none of them did it right. What they did was they showed that this is true for specific examples of p. So they said, all right, well, if p is a half, like they took p to be 1/2, plugged it in, and then showed that that diverged. And then they plugged in like 2 for p and then showed that that converged. But that's not what this says. This says it's for all p less than or equal to 1 and all p greater than 1. So you have to do a general solution here. Like you're never going to replace p with anything. All right, so I'm going to leave that to you. It's a bonus question, all right? Let's see how you deal with that. But the hint is that you cannot just use specific values for p, all right?
How much is this worth?
Normally, to be honest with you, bonus questions are usually worth different values depending on how many students turn them in. So if like everybody in the class turns in the bonus problem and they all got it right, then the bonus problem was probably kind of too easy, and it won't be worth as much as something like this where you only get like 3 or 4 people that turn it in. Then it's worth more. Does that make sense? So that also, like, you have to think about, like, if you work with people on it and like you all get it, it's worth less. It's better for just you to get it.
What if you negatively influence how they do it?
Yeah, you tell them the wrong answer. Yeah, you tell them the wrong thing. Yeah, you could sabotage them. That's fine with me. I don't care what you do. All right, so that bonus problem right there. And by the way, my in my class last week, some of the students were asking about, like, hey, are these notes, like, can we get these notes? And I'm like, okay. So these notes are online. These have been online all semester. So if you want to get to this, you can just go into Files in Canvas and Course Notes. It's all there. Yes?
I heard like so many things about lasagna in that video.
Yeah,
It's
yeah.
Like, what is going on?
Yeah, it's that class, I don't know. We used a lasagna analogy to do problems, yeah. You kind of have to watch them all to know what we're talking about.
You gonna watch season 3?
Okay, so our test is on Wednesday, right?
Yeah.
And it just so happens that with this class, your last topic that's on the test is today. So you're not going to have a whole lot of time with this idea. That's why I sent the lecture out last week, because I wanted to at least give you that opportunity to see it first. So we talked about type 1 improper integrals. In type 1 improper integrals, the main idea is that when your limits of integration are infinite, right? What we're trying to do is find the area underneath the function either going to the left forever or going to the right forever, or perhaps going both directions at the same time. So that's the type 1. Type 2 is very different. So for type 2, we call these discontinuous integrands. And the integrand, remember on a function, the integrand is actually that. Okay, that's what the integrand is. It's the function itself in here. So what we're going to be dealing with are functions that when we're integrating, we actually have a discontinuity somewhere within the interval we're looking. So we're trying to find the area, but somewhere in that region that we're looking, we have the function being undefined. And mainly what we're going to see is discontinuities where we have division by 0. Yes?
So if the domain is all real numbers, it can't be type 2?
If the domain is all real numbers on your integrand, then it's not possible to have a type 2. Correct. Yes, that is correct. So like an example would be this function right here, which we all know the antiderivative of this. It's not possible to have a type 2 on this one because it's impossible to make the denominator 0 unless you use complex numbers. So, okay. So let's look at some different scenarios that we could have. So let's say that we have a definite integral, right? So now this is a and b. These are not infinity, right? So let's say we're looking at some region. So if we look at our number line, we have a, we have b, and we got some function in here, right? Whatever. What if we have a discontinuity at a? So what if at a, our function actually has like a vertical asymptote, right? Now remember in college algebra when you have division by 0, or when you have like a rational function, you have 0 on the bottom, and then maybe the function is defined as like some constant on top. You get either like one of these cases going where your asymptote, your function either dives down or like goes up forever. Okay, so that's what we're looking at. What if that happens at the left endpoint? So at here, the function actually takes off like this. Now, vertical asymptote. So if you have vertical asymptote, what happens is you get closer and closer to it. As you get closer and closer, the function starts to take off. But we still do have area in there, right, the whole time? So the question is that area finite? Okay, so does it converge or does this area diverge? All right, so that's what we're looking at. Does it make sense visually? It's pretty much the same thing we were doing last time. Last time we were going along the x-axis, weren't we? We were going like this, and it was getting smaller and smaller, but we could talk about convergence and divergence. All we're doing is just doing it like vertically instead of horizontally. Okay, so we could also be doing a definite integral from a to b where our discontinuity is at the right endpoint, where at the right side it starts to go up forever, or it could go down forever, but either way we have this asymptote. So those are the things we could have, or perhaps, and this is the one that most people get in trouble with, is where we have a discontinuity within the interval. So maybe your left endpoint's fine, maybe your right endpoint's fine, but somewhere in between you have division by 0. So your asymptote occurs on the interior of the interval. In that case, you can see that we still do have area, and then we're going to have to figure out whether or not this converges or diverges. Make sense? Okay, so how do we do it? Well, just like we did before, we're going to use a limit to do it. All right? We're going to use a limit. So this first example here says, what if we have, or not example, this first note with a limit here, says, what if we have what if your function is continuous on bracket a, b, parentheses? That means that your function is not defined at b. That means your discontinuity is at the right endpoint. Then what would we do? Well, just like before, if we want to go from a to b, but this point b is where we have discontinuity, we will replace b with t, and then we will let t approach b, right? So that's just like we did when we replaced infinity with t and then we took the limit, we're going to replace b with t and let t go to b. But there's this one little aspect of it that we have to pay attention to, and that's this right here. So that has to do with the fact that when you're looking from a to b, right? So we're just looking in here, right? And we're trying to find the area underneath this function. Then if we're going to be approaching b, right? Because we're looking here, we have to approach b from the left side. And remember from limits in Cal 1, we have left-sided limits and right-sided limits. So this right here is a left-sided limit. It just says, look, we're going to be plugging in values that are getting closer to b, but they're coming in from the left. So they're always going to be a little smaller than b. And that'll be important with domains. You know, as we do the problems, we'll see some domain issues come up. But this left-sided limit will help us get around that domain problem, potentially. You'll see, just hang tight. All right, so that's how we deal with the discontinuity at the right endpoint. The next one is how we deal with the discontinuity at the left endpoint, and it's exactly the same. All we do is we say, okay, we have a problem here at the left endpoint, so that's A. So we're going to replace A with T, and we're going to let T approach A. This time, because we're looking in here, we have to approach A from the right-hand side. So that's why we have a little plus sign there. Now remember, because we're taking limits, limits either exist or not exist, right? It's one or the other. And if it exists, we'll say it converges. If it does not exist, it diverges. So we're going to have the same sorts of conclusions to draw at the end of these problems, either convergence or divergence. Now, this is the one I said is the tricky one. What if you have a discontinuity inside? All right, so what if you have, let's say this is A, this is B, but your discontinuity is somewhere in the middle, I'll call it C. Then how do you think we would set up this integral? Two integrals. Just like we did when we had like negative infinity to infinity, we broke it up into two. Here we're going to break it into two. So we'll go, first we'll break it up, we'll say we'll go from A to C first, so A to C, and then we'll go from C to B. And now each of these, right, on this one right here, where's our discontinuity? It's at C, right? So we're going to have to do a limit for this one. And then for this one, the discontinuity is here. We'll have to do a different limit. So we'll have two limits, just like we did with the negative infinity to infinity.
So then with that, would you solve it as the limit approaches C to the left?
Yep, we'll have to look at it, because this right here, like this would be our A and this would be our C. So we would be approaching C from the left. But on this one, it would be C here and B here, so we'd be approaching C from the right. So these two limits will be approaching C from opposite sides. We'll see this as we get into these examples. So here's our first one. And let's change this, because if you did watch the video, then, let's do something a little different. I won't change it much, all right? Let's just make this integral 0 to 1 of 1 over, let's just go x cubed. It's not that much of a difference. Okay, so I'm slightly tweaking the problem here. All right, so when you're looking at this problem, you have to be careful now. And this goes for all integrals now. When you have a definite integral, you need to make sure that you do not have a discontinuity anywhere where you're looking. All right, so we're looking between 0 and 1, right? So if we look between 0 and 1, we look at the integrand, f of x is 1 over x cubed. The only discontinuity we have for this function is when x is 0, right? X is 0, that's undefined. So we are looking on our definite integral between 0 and 1, right? So this is a problem. This is a problem right here. This cannot be in our function. We can't plug that in. But we can approach 0 from the left side, can't we? So to do this integral, we're going to replace, what? What are we going to replace? 0 with what? T, and we're going to take a limit as t approaches 0 from the right-hand side, right? Coming in from the right. And here's the integral. We're replacing that lower limit of integration, 0 with t, and then we're leaving the 1 up here because 1 is not a problem. And that's it, like that.
How important is the notation with T for points on the test? Because
What do you
feel
mean?
I feel like switching between T, C, and X, I'm just gonna want to just put it in
Can we
X.
just use the letter that's on, so like the bottom one is A and the top is B, so if we're looking for 0, can we just put it as A approaches 0?
You can, yeah, this is a dummy variable. This is completely up to you. Just don't use x, because x is already being used. Use whatever you, is that what you're asking also, or no?
Yeah.
Yeah,
So
you can use any, yeah, I'm just going with the notation the book uses, yeah.
But don't use X.
Don't use x, because x is already x is something different in the problem, right? X is your independent variable for the function. So you don't want to be letting x approaching this. That's not what this is our limits of integration, right? This is the thing we're plugging in for x, right? Yeah.
It'd already be in there.
Yeah, that would be problematic. I mean, I think for this one it wouldn't, because it's going to go to a number, but I would just not do it. I would just not use x. All right, what is the antiderivative? That's the next step, right? What's the antiderivative of that? So rewrite your limit, right? T is approaching 0 from the right. Okay, the antiderivative, remember that is x to the negative 3, right? That's what we're integrating.
Negative 1/4 over.
Negative, I think we got negative 1/2. X to the negative 2,
Oh,
right? Because we're adding 1 to this, right?
yeah.
So if we take derivative of this comes out, that gives me a 1, then subtract 1. Yeah, that's right. So that's our antiderivative. And we're going to evaluate that t to 1. Now, I did notice some students in the other class also trying to evaluate this right here, leaving it with a negative exponent, which is fine, but they were doing it incorrectly. So let me just remind you that that really means, how about we write negative 1 over 2x squared? Is that all right? Like just drop the x squared down with the 2. One more line. Limit t goes to 0 from the right. And what am I doing here? I'm going to plug in, right? So I've got 2 things to do here. So first we plug in 1, right? So if plug in 1 here, we just get negative 1/2. And then if we plug in t, we get negative 1 over 2t squared. Now what?
So you plug in numbers that are getting closer and closer to 0.
Yeah, we're gonna now take the limit. We're gonna actually try and figure out what happens as t approaches 0 from the right. So what we're thinking is, what happens when that right there approaches 0 from the right? Well, t squared, right, is going to go to 0, and it's positive because, well, you square anything, it's positive. So that's going to 0. 2 times something that's going to 0 is 0. The whole bottom is going to 0, right? Now, on the top you have a constant, negative 1. So what happens when you have a constant divided by a number that gets smaller? That whole ratio gets bigger, doesn't it? And so this whole thing right here, the whole thing, is approaching negative infinity. Now negative because that's negative, right?
Yeah.
A fixed number over 0, a positive number on the bottom. Shut up. Okay. Let me start this over. Let's say it this way. You have a negative number on top, right? And then this number on the bottom is a positive number. So the ratio of that is a negative number. But it's becoming huge, so it's negative infinity, right? But you still have a negative in front of that, and then you add negative 1/2. So it really looks like this, negative 1/2 and then minus negative infinity. So this thing is approaching infinity.
If we wanted to verify for our limits, we would put in the one that we already integrated, not the original function.
If we wanted to verify what?
Like the limits that we're taking, we would do it of the like negative 1/2 x to the negative 2, not of the 1 over x cubed,
What are we verifying?
the limit that we just took.
Mm-hmm.
So we would do it with the negative 1/2. Yes, we would do it with that, right?
Mm-hmm.
Okay.
Yeah, because sometimes we lose sight of what we're doing here. Let me go back and take a look here. This function, 1 over x squared, looks like this. Okay, this is what the function looks like. Sorry, x cubed. Oops, I changed it, didn't I? Sorry. X cubed, this one. It actually looks like this, all right? That's what this function looks like. And we're integrating from 0 to 1, right? So from 0 to 1, means we're trying to find the area. Let's say that's 1. Trying to find this area, right? We realize we have a problem at 0. So what we do is we replace this value with t, okay? So if I replace it with t, then I can find that area, right? What is that area? Well, that area is this, right? And then that becomes this. That's a formula for that area, right? Then what we do is we let t march its way towards 0. So what we're doing is we're sliding that bar, that line over, okay? So we want to be taking the limit as t goes to 0 of this formula, not of this, because that is something completely different. It's not the formula for the area, that's just the function itself. Does that make sense?
Yes.
Was that your question?
Yes.
Okay. All right. This okay? Now, what's kind of cool, not cool, actually it's not cool at all. Something to note. The bonus question that I just gave you, that one right there, says that the integral from 1 to infinity of 1 over x to the p, if p is greater than 1, what's it supposed to do? If p is greater than 1. It's supposed to converge, right? What was p in this problem? Well, right here, it's 3, right? But what happened? It diverged. Well, it's a different integral, right? It's not the same integral. This integral goes from 0 to 1. The one in the bonus goes from 1 to infinity. So if we were to be asking about this area instead, going this way forever, it would turn out in this problem that this would converge. That red area would converge, but this area over here that goes up like that diverges. It's kind of strange because it's like this is getting small fast enough that you converge to a finite number, but when you go this way, the area gets big too fast, and so it diverges. Does that make sense? It's like the rate at which this decays down is so fast that this red area converges to a number. But the rate at which this blue area grows is so fast that it blows up, becomes infinite. Yes?
Just a question, I don't know, I wouldn't do this on a test or anything, but I'm just asking if this is like, if this makes sense. Because you were saying you would slide the t over to approach 0. Couldn't
Yeah.
you conclude that it's approaching infinity just by doing that?
How?
Because you're saying if it's you're sliding the t over to 0, and
Yeah.
that makes sense. And wouldn't that mean it's you'd be able to tell it's going to infinity because the area is going to go up to infinity?
Okay, so with that argument, if I put a different function here, okay, that looked the same as this one, then you would draw the same conclusion, right? Like if
I'm not saying that I would just do that and say that's the answer, but I'm saying I could look at that and think like, okay, it's probably going to go to infinity, work out the steps, and then be like, okay, it's infinity.
Okay. I'm glad you're bringing this question up because you're actually tapping into the main idea here, and that's that if our graph looks like this, right? If I have a vertical asymptote and I go from here to here, we know that this area appears infinite. The whole idea of this is that sometimes it is, sometimes it isn't. All right? Yeah. My first example did what you think. It became infinite. The next example won't. And so if you draw the picture, you're going to, with that same argument, you're going to be like, as I slide that over, sure, it's going to get big, but it actually converges to a number.
Okay.
Yeah, so I don't know if that...
No, that makes sense.
Yeah. Yeah, so the whole idea here is that the area is going to look like it's infinite no matter how you draw it. But depending on the function itself, the integrand, that will dictate whether or not that area is finite or infinite. And it all depends on the integrand. Every function behaves differently. 1 over x cubed, this one, behaves in a way that that area between 0 and 1 blows up.
So with these limit problems, whether it's like these or the A to C, C to B, once we hit on an infinity, can we just say that it's divergent?
Almost. The question was if, like we just got infinity right here with that limit, right? As soon as we see infinity, can we be done? If you had two integrals and both of them are infinity and there's subtraction, then you have infinity minus infinity. Then you have to figure out what that might be. And you might have to do some factoring or L'Hopital or something like that. So in general, you can't say for sure as soon as you see an infinity, you're done. But once you've checked to make sure you don't have any indeterminate forms, then that's it. It's over. Diverges. If one diverges, the whole thing diverges. All right, let's take a look at this one. Let's tweak this problem a little bit. Let's just make this the cube root instead of the square root. All right? So let's see here. I think the most critical step now for us is to recognize that this could be an improper integral. If you're not thinking that way, then you might just start trying to do it the way we've been doing definite integrals, and that would be incorrect because we do have a problem with this function, right? Where's the problem? 2. At 2. So what we're going to do to start this, we look at the integrand. And we ask ourselves, is this ever undefined? Like, is there a number I can plug in here that's going to make this thing undefined? And I hope it's obvious that it's 2, right? If I plug in 2, I get 0 on the bottom. Division by 0 is not defined. So we have a problem at 2, right? And then we look at our interval, and we're going from, hey, 0 to 2, right? That's where we're integrating in here. So we have a problem at 2. And that means when I do this, I'm going to have to do a limit. I'm going to have to replace 2 with b if you want, right? Whatever you want. Yeah. Would you like me to? I'll do it. Yeah, let's do it. Okay. We'll be different today. All right. Limit. I'm going to let b go to 2. Now, which side are we going to approach 2 from? The left side. Okay? The left side. So when I approach 2 from the left, I put a little negative sign in here. And then I'm going to go integral 0 to b. Everyone understand I'm using b by request? Yes? I could use t. I could use the t, right? It's the same thing. And then I have 1 over cube root of 2 minus x dx. All right, so that's my setup. And now I have to integrate that, don't I? I have to integrate that. So this step right here of the integration, we might actually have to just come do the integration over here. Like we might have to take a little bit of time to like figure out the antiderivative. So I'm going to just go ahead and write this down. I'm going to rewrite this as an indefinite integral without the limits of integration, just so I can come get the antiderivative. And that might require, I don't know, integration by parts, trig sub. I mean, this integral can be anything at this point. All right? So let's see. How are we going to do this one? Just a basic U substitution. What would U be? 2 minus x, right? And then the du here would be negative dx, which means negative du equals dx. Hey, did I tell y'all last couple of weeks ago about me going to the DMV? No? Did I have to go? I thought I told y'all about that. I had to go to the DMV. No? Trying to get something done. I've been there 4 times. I'm hoping the 5th time will be the lucky. It's so, I mean, just the Leon Valley one. Yeah, that one does. Yeah. Anyway, no, it's just all that paperwork. The last time one of the documents I had was 3 days expired. I almost changed the date and went back. I almost went in my car and changed the date, but I didn't because I think there's stuff on it that says federal offense if you I love I'm trying again this week. That's why I'm bringing this up. I'm going to go for it again on Wednesday. All right. Well, what now? Rewrite the integral, right? So this becomes integral 1 over cube root of u, right? So can I rewrite that as u to the negative 1/3? Is that all right? Can we just do that now? and then this negative du, it's going to be like negative outside, and then du here like that. What is the antiderivative of u to the negative 1/3? 3/2 u to the 2/3, but I had that negative out front, right? So minus. So we're just adding 1 to this. We have to scale it by the reciprocal out front. Okay, and then replace. Let's replace u. So negative 3/2 u is 2 minus x raised to the 2/3. Right? Okay, that's the antiderivative. So now I come back over here. Limit b goes to 2 from the left of the antiderivative, which is negative 3/2, 2 minus x to the 2/3. I'm going to evaluate that from 0 to b. Keep going. Okay, this is going to be limit b goes to 2 from the left. And now I have my two things that I have to plug in, right? Let's see if I can squeeze this in here. I think I can get that in there. All right, first I replace x with b, right? That's the first thing that goes in. So this will be negative 3/2, 2 minus b to the 2/3. And then I replace x with 0, right? So this is going to be negative 3/2. 2 minus 0 is 2, so 2 to the 2/3. Now what? Take the limit, right? Let b approach 2. So if I let b approach 2, if that number approaches 2, I have 2 minus 2, which is 0. And so this piece, this whole piece is going to go away, isn't it? Now let me point something out here, because this is what got some of my students in my last class into trouble. Let's just say, just for the sake of making this point clear, what if that had been negative 3/2, 2 minus b to the negative 2/3? This was this instead. What if it was? If I take the limit and I let b approach 2, is this still 0?
No.
This is no longer 0. Because the negative exponent, that's the same as like negative 3/2 over 2 minus b to the 2/3, because you drop this down, don't you? And now when you plug in here, you get 0, but division by 0, well, that's a problem, right? So that would actually become infinite, because you'd have a fixed number over infinity, and, or sorry, over 0, that would become negative infinity, because that's negative. The whole point is that be careful, all right? If you got negative exponent, it's really a fraction. You have to take that into account. But because this is to the 2/3 power, it's positive exponent. This is approaching 0, 0 to any power 0, and then, well, 0 to any power except 0, right? 0 to the 0 is not 0. So 0 to any power other than 0 is 0, and then this is all 0. So this whole thing is 0, right? And then this one right here, this is just a number, isn't it? And that's what we're converging to. Okay, so let's see what this is. Well, negative and negative is positive, so this is going to be 3/2, 2 to the 2/3. Maybe we can leave it like that. We don't want to get a decimal out. We don't want to get our calculator and get a decimal, because that's just an approximation. We want the exact answer. That's the exact answer. So this means 2 squared cube root. So 2 squared is 4, so that's the cube root of 4.
That would be fine to leave it like that, not put a decimal.
Yeah, don't do a decimal, because, you know, it's like if let's say your answer to something was pi, that's the exact answer. If you say 3.1415, what you've done is approximated it, right? This is the exact answer.
So by doing that, you can make it less accurate.
That's right. That's right. If we went through all this trouble to find the area, the exact area underneath this curve,
Chop it off by like,
why approximate at this point? This is the exact area.
Yeah.
Yeah. Now, there are some times where it's not wrong. Like if you have 1/4, right? You could write 0.25, because those are exactly the same numbers, right? But if it's a repeating decimal, like 1/3, you could write 0.33 as long as you put a bar over it. That's exactly the same answer. But if your answer is the square root of 2, you can't do any decimal that's going to be correct. Everything you put will be an approximation because that decimal goes on forever and there's no pattern, there's no repeating pattern. Any number where you have a non-repeating, non-terminating decimal, y'all know what those numbers are called? Irrational numbers. So all irrational numbers cannot be approximated with a decimal. This is an irrational number. How do I know? I don't know, just experience, I guess, looking at it. It just looks irrational. Yeah. Just looks irrational. Can I go off on a little tangent for a second while we're talking about irrational numbers? Yeah, let's not talk about Leon Valley. I was very upset with that lady. She was just doing her job. I understand that. Okay, so irrational numbers. Rational versus irrational. I was actually talking to my daughter about this just the other night. I was. She's 9 years old. I wanted to try and get her thinking about this a little bit. Okay, I was putting her to bed and these are bedtime stories in my house. Yep. This is true. This is true.
Probably wakes up having like dreams about math.
I don't know. I mean, she likes math. I don't push it on her. I know this sounds like I do. I know it sounds like I do, but like, we have this thing that we've done since she was little, where at night when I tuck her in, she lays on her stomach and I draw on her back. I don't know any dads out there if you've ever, like I draw on her back and she tries to guess what I'm drawing. So like when we first started out, it'd be like, I would draw a T and she'd be like T, and then I'd try different letters of the alphabet and she'd try to visualize what I'm drawing, right? So now we've gotten to the point where I'm drawing linear equations. I'm like drawing these types of equations on her back, like
Sitting there like irrational.
like I'll do the time. So I'll do like 3x plus 4 equals 7 times 3, and then she'll like tell me what to write next. She'll like, okay, next line, and she like works it all out like mentally. It's awesome. I love it. But she likes this stuff. I don't know. She's like, let's do equations tonight. Okay, so this isn't that far out of the realm. I was trying to talk to her about irrational and rational numbers, but I was making it a much more kid-friendly conversation. She's 9. Yeah. Yeah, she's pretty smart. I mean, she knows all her perfect squares, like 1 squared, 2 squared, all the way up through 18. So you can ask her like, what's 17 squared, and she's got it. She's known that for about a year, and we're working on perfect cubes right now. But cubes get hard. You get up past about 5, 6, and they start to get pretty big pretty fast. She just likes it. I'm sorry, I'm not forcing it down her throat. Okay, look, rational versus irrational. So do we all understand that when we look at a number line, that this number line is solid? That there are numbers between 0 and 1, like there's a point anywhere in here, right? There is a number that represents that position, yes? Okay, so the whole number line is called the real numbers, right? Real numbers. The whole number line. Now, there are 2 types of numbers in here. There are only 2, all right? There are only 2 types of numbers. There are rational numbers and irrational. Those are the only 2 groups that exist here. The rational numbers are all of the fractions. Every fraction you can think of. So, is 0 a fraction? Yes. 0 over 1, right? That's 0 over 1? Okay, how about 1? Is 1 a fraction? 1 over 1. Okay, how about 2? Is 2 a fraction? Yeah. 2 over 1. Okay, so all the integers, all the counting numbers are there, right? You could do all the negatives, -1, -2, right? Then you could do all the other things that you can think of fraction-wise, right? Like 1/2, 1/3, 3/4, all day long. You can sit here, right? There's an infinite number of fractions in here. Yes? Okay, but along with those, there's this other category, irrational. So I know some of you are familiar with these. Can someone give me some examples of irrational numbers? Pi. Okay, so pi is irrational because it is 3.1415, and this keeps going, and there's no pattern to it, and it never stops.
Yeah.
E is an irrational number. I'm going to say approximately 2.718. Goes on forever, no pattern to it at all. Any others you can think of? Square root of 2 is an irrational number. It's approximately 1.414. It goes on forever, there's no pattern, never stops. Okay?
Cube root of 4.
Yeah, I mean there's a lot of these, right? Now there's a lot of these, right? There are an infinite number of these. It turns out that there are an infinite number of these also. Right? Would it make sense to you that that would be true? Now, when I was learning irrational numbers, I was given a few examples. And so I always had this belief that there was like less of these than these, because people would only tell me about maybe 4 or 5 of them, right? Okay, but what I'm about to tell you, it's kind of mind-boggling. There's an infinite number of these, right? There's an infinite number of these. But there are 2 types of infinity, right? We have 2 types of infinity in our number system. We have what's called countably infinite and uncountably infinite. So I like the analogy I like to use is think of like a pond, okay, with lily pads on it. Think of an infinite pond, a pond that just keeps going forever. And you have lily pads that are going from this end of the pond to the other end, which is infinite. These numbers right here, these fractions, right, are like the lily pads on the pond. You could start walking from one lily pad to the next. So you can actually walk from one number to the next. There's a way to walk your way through the fractions. Now, you'll never get to the other end of the pond because it's an infinite pond, but you're always able to walk your way across. Does that make sense? Okay. Irrational numbers, you cannot do that. All right? So there's not a way to start at an irrational number and take your step to the next one. Because as soon as you take your step to the next one, you realize that you missed not just one, you actually missed an infinite number of them. So you try and step back to one of them, then you realize you missed an infinite number. And it's very difficult to explain this. So the analogy that I've always used is, do y'all remember? No?
Ooh, we're talking about
Okay, I may not have, okay. So,
you just told us that there's a lot more irrational than there is rational.
yeah, there's an uncountable infinity number of these. There's countable. So this is the best analogy I have for it. Have you ever just been way far out of the city, away from the city lights, and you look up at the sky at night and you just see stars like everywhere? Has anyone really seen like a true Milky Way through the sky before? Okay, I mean, it's unbelievable. Well, if you ever get the opportunity to do that, when you're looking at the stars, I would like for you to think of the stars as the fractions. Okay? So you look up there and you just see, I mean, they're just everywhere, right? Stars everywhere. Almost seems like everywhere you look, just stars. And if you, oh yeah, there was one there. It's just, they're everywhere, right? There's like an infinite number of stars out there. Now, are there? We're not going to debate that right now. But I'm just saying this is a visual type. So the stars are the fractions. These are what then? Not the ones you can't see. It's the darkness. It's the black up there. Okay? So it's like, it's everywhere, but it's impossible to see one, like to point out one of them. Because how do you point one of these out? You can't ever like nail it down because this keeps going and changing, right? Yeah. So it's like, if I could point, like if I had a perfect pointer, I could maybe point to a star, right? I'd have to be super precise though, because if I'm off a little bit, I'm not at the star, right? Yeah. So how can you point to pi? Like it's there, but I can't get to it. You know what I'm saying?
You can't like nameless point in the blackness of space.
Exactly. It's impossible for me to get my pointer on, but I know it's there. And there's all the blackness represents all of the other ones. So you have this true difference in the type of infinity we have here versus here. Does that kind of make sense?
That makes sense too, because like space is always expanding.
Yeah, we'll see, that's theoretical. So that part, I can't make the analogy. This is visual completely. Because you could argue with me that there's a finite number of stars, right? You could argue that, and then this analogy goes away because there's an infinite number of
I'm
these.
just saying that, supports
Yeah.
your analogy.
Yeah, we could probably build it up a little bit more, but okay. So the irrational and the rational. Now, I wasn't trying to explain that to my daughter. What I was trying to explain to her was that.
The lily pad?
No, I was trying to explain to her. She has an aquarium. She has different fish in the aquarium. So I was trying to explain to her, like, some of the fish are like integers, like types of numbers. We have different types of numbers. Oh, this fish is, what we call what did I say? Natural numbers, counting numbers, whatever. And then I said, oh, and that one special fish you have, that's an irrational number. So I was trying to tell her there's different types of numbers, just like you have different types of fish. But the more important point, and this is what I want to point out to you also, is that if our fish tank are all our real numbers, right? So if this is our fish tank, right? Well, that's not all of the numbers that we have in our mathematical system. There's actually other numbers out here, double script C. These are the complex numbers. So what I was asking her was, I asked her, hey, do you think your fish, she has a fish named Lenny, that's her favorite fish. I said, do you think Lenny knows about our dogs? We have 2 dogs, Zeus and Little Bear, okay? These are not my names. All right, Zeus is mine, sorry, Little Bear is not mine. So I said, do you think that Lenny knows that Zeus exists, that Little Bear exists? And she's like, no, and I think I made the point. The numbers that we work with in our number system, the real numbers, okay, what we are familiar with, we are living in a fishbowl. There is a bigger universe out there of complex numbers. And it turns out that every fish is a complex number. Every number on this number line is a complex number, but it lives in a bigger system. The numbers out here, the things that live out here, are still numbers, but they're not these types of numbers. And when you look at mathematics from the big picture, you can take very difficult problems, whereas when I say difficult, if all you can ever see in your world is the fish in the fish tank, and that's all your whole universe, you can come up to a problem that you just can't do. You just cannot get through this problem. Mathematically, there's just no way through it. But if you actually step back and realize that problem lives in a bigger system, you can attack the problem from this point of view, and you can make it a trivial problem, like a 2 + 2 is 4 problem. So complex analysis is super important in mathematics because you can do very difficult problems in here using this outside perspective. That make sense? Okay, so if you ever see this I is equal to the square root of -1, if you ever see that and it's like, oh, imaginary, it's all made up math, absolutely not. This is critical. This is all part of this. Imaginary numbers are very useful. You'll see that as you move on, that we use complex analysis to. Because when they were first thought of, it was thought that it was kind of ridiculous. Truly, it was. Yeah. Because the imaginary number originally came from the idea of trying to find the roots of a parabola. Right? So what are the x-intercepts of this parabola? There are none, right? But if you use a quadratic formula, in the quadratic formula you have that piece right there, right? Right? That's negative b. Plus or minus square root, that's the quadratic formula? Mm-hmm. So if you say, hey, here's a parabola, and go find its x-intercepts, and you use this formula, this will turn out to be a negative number, right? And so you say, okay, there are none, right? And it makes sense visually, like this corresponds with this. What was discovered later is that for cubic functions, you have another formula. There's a different formula for cubic functions, and it has roots in it like this. And it was shown that there are times where you get negatives under roots using the formula for the cubic, but all cubic functions have to look like this. That, or they could go this way. But cubed, remember if you cube something, the left side goes down, the right side goes up, or the left side goes up and the right side goes down. It's one or the other. And no matter which way you do it, you've got to have x-intercepts. You've got to. So that means the square root of a negative had to make sense somehow. So that was a major breakthrough when we realized that the square root of negative numbers actually had to have a meaning because that graph had to have a solution. Yes?
There's a video of that on YouTube that shows it visually with a graph in like three-dimensional.
For what? For this or for that? For the,
The imaginary number where
Yeah.
the parabola crosses the x-axis.
yeah.
Where it shows that when you expand it out, it actually goes down.
Yep. There's so much stuff on YouTube, man. I wish I would have been a student. I wish I was a student nowadays, because when I started getting really interested in math, there was no resources like that, you know. Now, of course, it's also equally filled with garbage, but, you know.
Where are we gonna start working with complex numbers?
Good question. Complex numbers, unless you're in a math sort of thing, well, I'm trying to, what's your major? Engineering. They're going to probably start bringing it in I would say somewhere in engineering analysis, maybe engineering analysis 2. I'm not sure where it comes in there. But engineers do use it. I mean, it is, but not they don't get like a full-blown treatment of complex analysis. Math majors actually take a class called complex variables. So they start off kind of like, it's like a college algebra for complex. Then they do all the calculus in there. Okay.
So are you teaching your daughter complex numbers at the age of 10 then?
In some way, you could say that I've introduced her to the complex.
She should listen to her.
Yeah. Okay. What is her grade in math? I don't know. I mean, she doesn't. She does very well academically. Yeah. We don't force. We actually tell her like chill out. Like chill out. You know, go play. Go play. Yeah, exactly. Go play. All right. All right. So we're done with that one, right? So we have an example that converged, right? We had divergence, now convergence. I'm afraid she's going to be that kid that's like so good until she like hits puberty. And then she's going to be like that rebel, that rebellious kid that, you know, her boyfriend comes up with a motorcycle and, you know. I can already see it. All these great years. She's going to, you know, the yin and yang is coming. I feel it. Yeah, right.
This is your rite of passage.
Yeah.
Partial fraction.
All right, yes, so here we have, do we have a problem here? See, this is the thing I think that gets lost, especially when you're sitting there and you're stressed out taking a test. You start to lose the like whole idea of checking to make sure you don't have an issue. So when we look at our integrand here, I'm going to factor the denominator. And the reason I'm factoring it is if I factor it, then it's easier for me to see where it's undefined. So that function is undefined where? 0 and 4, right? 0 and 4. And if we look at our number line, we're going from 1 to 4, right? So we have a problem here at 4. Now we also have a problem at 0, but that's not in our interval, so we don't care about it, all right? So we're only interested in the 4. So we're going to go limit B or T. I'm going to go back to T. I like T. I don't know why. All right. I like sweet tea also. T approaches 4 from the left. And we're going integral 1 to T. And we're integrating 1 over, I'll go ahead and factor it, x minus 4 dx. Now I factored it because I'm going to do partial fractions, which reminds me, I graded your quizzes yesterday. They were good. They were real good. I think everybody got at least higher than a 70. Let me pass these back. The grades are not on here, so I don't think anyone will have a problem with me handing these out, right? But all you have to do is add up the numbers, you know, however many points I took off, subtract it from 100, that's your grade. So if it's just minus 7, you got a 93. I want to just say something real quick about that. And this happened in my other class too. I saw some people doing some integrals some very, very strange ways. Not strange, I'm not quite sure if those students got help, which I told you you could. Okay, so I'm not calling you out, you were getting help. But the method that was used was so kind of different than anything I showed in class. It just kind of concerned me a little bit because, and I wrote on those students' pages, like, yes, this works, but wow, I mean, like, this is a lot of work. Like, there was one student that did, the first problem was a little messy. But I think that one student, it took like 4 or 5 pages to get to the answer. Well, I mean, no, everything looked pretty okay, but it just seemed like, wow, why not just do what we did in class? Like, why not just, because number 1 was the one where I told you to like introduce the magic thing. That saves you a lot of time long term if you do that. And then also, I want these to get around. You know what, why don't I wait till these get around, then we can talk about them a little more. Let's just get back to this. We have to do some integration here. I'm integrating this. Okay, so how do I do this again? I forgot.
Oh, you do the A.
Yeah, so I need to look at this thing right here, and I have 2 distinct linear factors. So a over x, and then b over x minus 4. Because they're both linear, I just do a and b. And then I can clear out the fractions. And then to do the rest, you could expand it out and use the long method, or you could pick some values of x and do the short method. Either way. Short probably would work pretty fast, but I did the short in the other class, so I'm going to do the long in this one. Let's see. I think it's going to work so quickly, it's not going to matter. So I just distribute the a, collect my x terms together. So I put my x's together, factored out an x. So from this, I know that a plus b must be what? What's the number in front of x over here? 0. And then that means negative 4a must be 1. So you should get that a is negative 1/4. And then when I plug that in here, if I plug negative 1/4 in here for a, then move it over, I get b is positive 1/4. Y'all okay? Y'all both have the same exact look. No, y'all both looking exactly the same at this. Y'all are like, you sure? You all right? You got it? Okay. All right. So now I have limit. T is approaching 4 from the left. Now the antiderivative. Oh, crap. I never took the antiderivative. Okay. Yeah, I did the same thing on the other video, didn't I? Okay, so let me rewrite this integral. This integral is now the integral. A is negative 1/4 over x plus b, which is 1/4 over x minus 4 dx. Let's get these antiderivatives. What is the antiderivative of negative 1/4 over x? Negative 1/4 ln of absolute value of x. This 1/4 can come out, right? And then I'm taking the antiderivative of 1 over x minus 4, which again is natural log. Be careful with that natural log. I saw again on this take-homes, some people are just like firing away. Whenever they see 1 over something, they just go natural log, no matter what it is. So like I saw people integrating 1 over x squared, plus 4, and saying that that's natural log of x squared plus 4. I mean, it happens. That's very common. Just be careful. I mean, that only works if this is, linear, or if the derivative of it is up there also, and you can do u substitution. So, all right, that's our antiderivative, yes? Okay, so that goes over here. Negative 1/4 natural log x plus 1/4 natural log of x minus 4. I'm going to go ahead and put that in parentheses and then put my evaluation bar here. I'm going 1 to t. Can I erase this up here? Is that right?